Tonight we open Earth's oldest vaults. Ice 2 miles deep, mud from silent oceans, and rocks that remember fire. You'll see the real tests scientists use to tell stories from the past. Tiny ash lines, odd carbon shifts, and clues smaller than a grain of sand. No wild claims, just clean, shocking evidence you can picture in your hands. Are we truly the first? Or is there real proof someone was here before us? Listen to this claim. We finally know there was a civilization before us. It sounds huge, like thunder rolling over a quiet field at night. Your heart jumps. Your hands feel a little cold. But before we believe, we test. Science first, story second. The honest truth right now is simple. We have no proof of a high-tech people before humans. None. Still, the question is worth asking, because the ground keeps secrets. Rocks stack like pages, one on top of another, a page for each year. A library 4.5 billion years tall. If someone lived long ago, their mark would not be shining cities. It would be tiny things that last. A thin ash line, a change in carbon by a few parts per thousand, a strange dust grain the size of a pinhead, a hint of metal where it should not be. Picture a clean glass jar of air with numbers written on it. Picture a core of ice, 2 miles long, cold as the dark of space. Picture mud from the deep sea, laid down one quiet layer each season. These places hold time like a vault. Tonight we open that vault with calm eyes. We compare bold claims with careful facts. We listen to the rocks, to the ice, to the oceans. If a hidden chapter exists, the pages will whisper. If not, the silence will teach us too. Either way, we learn what our own layer will say about us tonight. Here is the fair question we have to face. If a past high-tech people were real, how would we even know? Scientists give this idea a careful name, the Silurian hypothesis. It does not say they existed. It says let us test the rocks, the ice, and the mud, and see what would remain after a million storms. Picture a lab at night, lights low, a core of mud on a steel table, 1.2 meters long, wet and dark. A tiny drill hums. Grain by grain, the past comes out. We look for signs that match industry, not volcanoes. Carbon ratios off by a few parts per thousand. Fly ash spheres the width of a hair. Odd nitrogen from heavy fertilizer. And man-made atoms made after 1945. We also hunt lookalikes, since nature can trick us. Lava makes glass beads. Impacts spread iridium. Cold seas shift gases by themselves. So we stack clues, demand repeats, and check dates twice. The rule is simple. No single hint is enough. The case must click like a lock with many pins. If a hidden civilization left a mark, these pins will set together. If they do not, the click we hear is noise. Start with what would last when everything else falls apart. Cities crumble in decades. Steel bridges rust out in a few thousand years. In a million years, only dust remains. But chemistry can stay. So we list the clues that could ride through time. First is carbon. When oil or coal burns, the carbon has a light fingerprint. Scientists can spot a shift of only a few parts per thousand in shells, mud, and tree rings. Next is ash from smokestacks. Under a microscope, it looks like tiny glass beads, 10 to 50 micrometers wide, black like burnt sugar. These beads settle in ponds and seas and make a thin gray line you can measure with a ruler. Then come plastics. Sun and waves break a bottle into bits smaller than a grain of salt, but the pieces still keep the shape and shine of plastic. In cold, deep mud, those bits may sit for millions of years. After that is the bomb signal. New atoms made after 1945, like cesium and plutonium, sink into soils and snow and tell clear time with half-lives counted in years to thousands of years. Fertilizer leaves heavy nitrogen. Lead from old gas leaves a special mix of isotopes. None of this looks like a building, a road, or a phone, but together it reads like a tag on a shirt, made by industry. If another people once burned, built, and mined like we do, this is the trail they could not hide. To see what a tech layer looks like, we can read our own. Walk into a clean lab with humming fans and white lights. On the bench sits a tube of lake mud, 92 centimeters long, capped tight. A thin wire saws down one side. The smell is leaves and iron. Slice by slice, the years stack like stripes on a candy cane. Near the top, the story gets loud. Tiny black spheres appear under a scope, 10 to 50 micrometers wide, smooth, glassy. They are fly ash from coal fires, the breath of smokestacks. Mixed in are blue and green shards that do not belong to sand. Microplastics. Scuffed and bright even at 100 times zoom. A magnet pulls out specks that cling like pepper to a magnet stick. Those are industrial bits of iron and nickel. Next, the gamma counter ticks faster. It finds the bomb spike, new atoms born after 1945 like cesium-137 and plutonium-239. Their half-lives mark time as clearly as ink. A chem run shows nitrogen a little heavier after the 1960s, a sign of fertilizer feeding fields. Lead isotopes shift too, proof of past leaded gas, then a clean drop when laws changed. All of this happens in just the top few centimeters, the last 100 years or so. The great acceleration set in mud. If someone far in the future asked, "Were people here?" this band would shout yes. Now we ask a harder thing. Do any older layers whisper the same? Nature can fake many of the clues we seek, so we have to be careful. Volcanoes toss hot ash that hardens into tiny glass beads, 10 to 50 micrometers wide, almost the same size as fly ash from smokestacks. Asteroid strikes scatter spherules too, plus iridium dust that shows up as a bright spike when the lab machine hums. Wildfires darken lake mud with charcoal flakes thinner than a hair, and rivers wash old soils that nudge carbon by a few parts per thousand. Cold seas can burp methane, and that push can swing carbon light, much like burning oil would. Quiet, breathless oceans make black shales rich in iron, nickel, and sulfur, a mix that can look industrial at first glance. So we separate lookalikes with many tests at once. Volcanic beads carry more crystals inside. Fly ash spheres are smoother and richer in carbon. Impact layers hold shocked minerals, and a thin blanket spread the same day worldwide. Industry rises slowly and peaks over decades. Methane events come with fossils of warmth, loving plankton, and a pattern that lasts thousands of years. Factory signals jump fast, then fall when laws change. Bomb-made atoms such as cesium-137 and plutonium-239 have no natural twins in deep time. Plastics keep their changed shape under a scope. No rock copies that. A single odd hint is never enough. We want a stack that fits like gears. If nature wrote the line, the gears slip. If people wrote it, every tooth will click. Open the rock record at a loud page we know well. 66 million years ago, a thin clay line shows a sharp spike of iridium, far above normal in Earth's crust. Mixed in are glassy spherules, tiny as dust, and grains of shocked quartz that form only in huge increments. Follow that line to a round scar on the map, the Chicxulub crater, about 180 kilometers wide. Rock, spherules, and crater tell one clear story. An asteroid hit, the sky went dark, and the dinosaurs died. Turn more pages back to 252 million years ago. Here the pages darken. Basalt from the Siberian traps poured out in layer after layer, making flows across Siberia. Totals may reach millions of cubic kilometers. Carbon in shells turns lighter by several parts per thousand. Oceans lose breath, and most life vanishes. The pattern fits long, massive eruptions that pushed heat and gas for thousands of years. It does not fit a short, sharp industry pulse. Another page shows the PETM, about 56 million years ago. Global warmth jumps by 5 to 8 degrees. Carbon grows lighter again, soils blush red. Tiny seashells thin and start to dissolve. The rise takes a few thousand years and fades over 200,000, steady like a slow drum. These famous layers are our rulers and clocks. They teach how volcanoes and space rocks mark Earth. If a tech layer existed, it would stack different clues together and sit in a different time band. Start with places that save quiet layers. In the deep ocean, from storms, fine mud settles like dust on a shelf, maybe 1 millimeter each year. At 4,000 meters down, it is cold, black, and still. No oxygen to chew the record. That makes a steady book we can read. Varved lakes do the same on land. Summer lays a light band, winter lays a dark band. Count them like tree rings, and you get exact years. Caves grow stone drips called speleothems that lock in signals drop by drop, carbon writing lines. Peat bogs stack plant bits in brown, wet bricks that keep pollen, soot, and beads. Deltas bury dust fast. 10 to 50 centimeters in a single flood, then seal it under new sand. On ice caps, wind traps snow into layers thin as paper. We drill 2 miles down and lift blue cores that hiss in warm air. The gas bubbles inside tell us past air to the part per million. Coral reefs add 1 millimeter of skeleton each year. Their bands hold warmth and carbon changes. Tree rings remember droughts, fires, and metal in rain. Across all these places we use the same rule. We want steady clocks, pages, and low mixing. We map sites across continents so one blip will not fool us. If a text signal hides in time, it should appear together. The light carbon, the fly ash, the plastics, the bomb spike. If it does not, the silence is the answer. Now we read the pages we already have. In polar ice, cores reach about 2 miles, with clear layers back roughly 800,000 years and new work pushing past 1 million. The bubbles say the air rose and fell, but they do not show plastic dust, bomb atoms, or factory gases before humans. In lake mud and deep-sea ooze, the top few centimeters shout our age. Fly ash, microplastics, nitrogen, lead shifts, and a 1963 bomb peak. Below that, the voices fade to the slow tones of nature. Clay turns, shells thicken, colors change with warm and cold. We see the Petium slow rise and long fall. We see ash from far volcanoes counted in milligrams per kilogram. We see wildfire soot spread thin as smoke. But we do not see a sharp stack of human-type clues deeper. Stone drips in caves keep bands, with carbon lines that bend when rain or plants change. Peat bricks hold pollen maps that track forests moving by meters a year, not factories. Corals grow 1 millimeter a year and show waves of heat and chill, not jumps from engines. When we line up sites on 3 continents, picture agrees. Nature drew these lines. The tension stays because a gap is not proof, but each test lowers the odds. If a hidden age once lit the world, it left nothing we can measure. So the next step is simple and hard. Keep drilling, keep checking, and accept what the pages say. This question still matters because it turns our eyes back on us. Someday our layer will be the page someone else reads. What will they see in the top 5 centimeters of mud, or the top 3 paper-thin lines of polar snow? They will see microplastics, fly ash, the 1963 bomb spike, and lighter carbon in shells. They may smell oil in a wet core box, like a cold garage at night. That picture can be dark, but it can change. Science is not only a mirror, it is also a tool. We can choose what our layer says. Think of simple switches we control. When rules changed about leaded gas, leaden rain fell fast. When scrubbers went on stacks, the ash bands thinned. River laws cut mercury in fish by half in a decade. These are small gears we already turned. New gears wait. Cleaner power lowers the light carbon drift by parts per thousand. Better soil care eases the heavy nitrogen line. Less plastic use trims bright shards in lake mud. Each move writes a kinder sentence. There is also wonder, not just worry. Our layer holds cures, art, maps, and stories. It holds a promise that we tried to leave the house tidy. Picture a future student in a room at 2 a.m., lamp, snow falling outside, reading our century like a letter. Will that student nod and smile or wince? The rocks will be honest. We still have time to edit the line they read. Here is the clear ending, said Plain. We searched ice 2 miles deep, mud laid a millimeter a year, rocks that hold shock. We looked for the full stack. Light carbon by a few parts per thousand. Fly ash beads 10 to 50 micrometers wide. Plastic crumbs and bomb-made atoms with half-lives that tick like clocks. We did not find that stack in deep time. The pages show volcano fire, sea burps of methane, and one great rock from space. They do not show a short, sharp tech band before us. This is not dull news. It is strong news. The test works and the door stays open. If a hidden layer waits, the tools can catch it. If not, the silence is an answer too. So we end where we began, in a quiet lab with fans and blue light. A core hisses as warm air touches it. A meter stick rests on the bench. Numbers in small lines, ppm per mil, years, glow on the screen. The team writes notes, checks dates twice, argues gently, and lets the data win. Truth like this is not a shout. It is a steady drum you feel deep in your ribs. Are we the first? With what we can measure today, right now, yes. Could new drills, new eyes, or new math change that? Maybe. For now, we hold two things at once. Wonder big enough for wild ideas, and care sharp enough to test them. That is how real stories end and begin.